Today, we're going to start chapter 4, which basically talks about applications of the derivative. We're going to talk about maximum minimum values today. This is incredibly important. In fact, one can argue this is a big central part of what calculus is all about, finding maximum minimum problem. As you can guess, this is very important in engineering and science. I mean, oftentimes we want to do to maximize something. When is something optimal? When is it as big as possible or as small, as efficient as possible? Something like this. So understanding this is an important piece of the puzzle. So let me start you off with the definition. Let f of x be defined on some domain D. So this is just a set of real numbers. It's the domain. It's basically the stuff you can plug in, or that it's okay to plug in for f of x. And this domain contains C, some real number C. If the value of the function C, so when you plug in, you get your y coordinate for C. If this happens to be greater than or equal to every other value of the function, all x to d, then the y coordinate here is the absolute maximum. For f of x. If, on the other hand, this value is smaller than or equal to f of x for all x and b, then f of c is the absolute minimum value. So, let me give you some examples. So here. This, but if this is my function, then this is the absolute minimum. But notice the y coordinate here is smaller than every single other line. The absolute maximum is about here. That's just the biggest y coordinate, right? And it's a simple sign. That's what absolute and absolute max is. It's the smallest and the biggest output of the function. Now, you let d equal all the real line, then if you let f of x equal x, what's the absolute maximum here? There isn't, right? Because no matter how big you think you're going to get your y coordinate, get a little bit bigger, move further to the right. No matter how small you think you make the y coordinate, I'll get it to the left. What if we have sin x? What's the maximum? Right, well, so the maximum actually is one, 'cause that's the Y value. And it occurs every so often. It occurs with pi over two and 5 pi over two, negative 3 pi over two. So the maximum is one, and it occurs infinitely often, right? What about the minimum? Negative one, also occurring infinitely often. A function might have a maximum and no minimum. So, all you have to do is use your imagination here. You have a function that looks like this, which is my rendition of the sort of thing of bell curve. Notice that this function here has a maximum that occurs right there, but it appears to have no minimum, right? Because it sort of gets smaller and smaller, never getting to zero. Right, okay. Can anybody give me an example of functions just on a finite interval because they are maximum? How about this? What if I did this? So what if this is sort of a vertical asymptote? And then there's no point. But everybody agrees that there's no minimum, right? Because no matter how low you want to go a little lower. And there's no maximum because if I colored in that point, the maximum would occur right here, right? There's no point. So again, you've sort of got the same problem, just on a smaller scale. Okay, can anybody give me an example of function that is on the finite interval and is defined interval? Notice this function is not defined here or here. So suppose I have a function like this. Let's say it's defined above input. Anybody tell me how I can make a function that has either a maximum or a minimum? What's up, middle? Max. That. I did say I want a function on everywhere. So I'll do that. See how evil I am, right? This function is on a finite interval. And it doesn't have a minimum, right? Because it would need to have this point that's out of here, that you have the minimum, and it doesn't. I cheated and I slid that into the middle. It also doesn't have a maximum, you need to have this. I took what it needed here, what it needed here, and put it in the middle. What's different about this function as opposed to this one or this one? What's all these functions here? This have a nice property that this crazy broken. No, too close. It is defined everywhere. No matter what x coordinate I have, I do it in mind. You're on the right track. It's not continuous, right? I'll allow jumps and breaks. In continuity, function being continuous is going to play an important role. We can see from this example, this is continuous on the open interval, but not defined on the endpoints. This is continuous on a big interval. It's going to turn out, you know, a function that's continuous on a closed interval. So this is an example. It's defined everywhere on the closed interval, and it's continuous. It has to have its maximum and minimum. Okay. Let me go ahead and do this theorem here. This is called, this is often called extreme value. So, terminology here. Absolute maximums, minimums are collectively called absolute extreme. So the word extrema or singularly extremum refers to just collectively maximum or minimum. We'll refer to as collective. There. This extreme value there. And I cannot prove this because this requires a couple of subtle things that are sort of beyond the scope of what we're doing in this particular course. But this theorem, I think, is extremely intuitive. If f of x is continuous, well, then let's suppose that a being less than b, less than b, then f of x attains its extreme values. So let me draw you a couple of pictures just to try to illustrate this. So it has to be a closed interval, and I have to be able to draw this. I have to be able to draw this without picking up my marker. Notice that this attains extreme value. Notice this is the min, right? The absolute minimum on that interval. And it looks like it attains the maximum here. Another example. Close interval. Yes. In this case, what are the extreme values attained? At the end, right? Or you might have this. Possibility. So it's possible to obtain, let's assume that the y coordinates here are the same. You have mins here. Here, this is an example, and this is what this theorem says. If you draw any continuous function, that'll be continuous, and it's gonna be on a closed interval, then there has to be a place where you've got a max and a min. If you remove closed, if I have an open interval like this, so I don't have the endpoints, all I have to do is something like this. I don't have much. And we saw, remember my broken function example? That's a good example. If you remove continuous, it doesn't work either, or it doesn't necessarily. Now, let me point out. Let me point out the following. What the extreme value theorem says is if you have a continuous function on closed interval, then you have extremes. It doesn't say it the other way. It is possible sometimes to have extreme values, even if you're not continuous, for example. So you have this. You can certainly have, notice this function is not continuous, but you certainly do have the max and the min. So it's possible to get lucky, right? But what the theorem tells you is, you know that if it's continuous on the closed interval, you don't have to get lucky at all. Okay, any questions? Okay, I'm gonna move on to something a little bit more helpful, but if you look at these three pictures, this one, this continuous function on closed interval, do you all see pattern of where these extreme values are from? Right, so look at these. What seems to happen a lot? Might classify where the extreme values occur in a couple of ways. One way is they occur at the end of the interval. You see this right here, this min occurs right at the end point. You see this here, where both the max and the min. So we've got that. It might occur. If it doesn't occur at the end point, can you describe what it looks like? Where? Right. It looks like you either have a max or a min occur at the end point, and if it occurs somewhere inside, it's on the top of a mountain, or it's in a place that holds water. Right? See that pattern? By the way, there's something else to notice of this. What do you think? Notice what happens. Well, actually, let me get that. I want to describe tops of mountains, places that hold water, right? Notice this one right here has arguably one, well, maybe not this one, but it's got 1, 2 tops of mountains, right? And maybe it's got one place here that holds water. This one has 2 places that hold water and 2 tops of mountains. Right? I want to somehow define these things. These are actually called local extremes. Notice, I'm going to write this down carefully. Notice that what you have here is a top of a mountain. This is a candidate for being the biggest all around, right? Right up here is the biggest kid in the neighborhood. There's a tougher kid over another neighborhood, right? These two right here tied, but notice that if this dipped down a little bit lower, this would be a minimum in a small little region, right? And you think, if you didn't go very far, you think, okay, this is as low as it goes on the Death Valley. But it's possible that it went lower over here. If a big minimum. So this is the idea of what we call local extreme. That sometimes it's called relative extreme as well. If there is an interval, this is just some interval containing C and C. And when I say that, I mean C is interior. That is, when my interval contains C, I want C to be somewhere inside there, not an end. And f of x is less than or equal to it. Say f of c for all x I, then c f of c is a local max. This is not necessarily the, it's not necessarily the absolute maximum, it's a local maximum, right? So for here, the interval might be this. Notice that the x coordinate corresponding to the red point is inside this interval. And this is the biggest kid in there. That's what it means to be the local max. The biggest kid, do the local check. Right? For example, this is a local max. In fact, both of these are local maxes. Because you've got a little interval here where this is the biggest kid in the neighborhood. You've got an interval here where this is the biggest kid. And you might expect this from x local then. If in I f of c is less than or equal to f of x, then c f of c is local minimum. And once again, we refer to these local extrema collectively as what we refer to these as local extrema. Okay. Let me give you. Here. Let's grab this. I'm gonna break all my mathematical skills to bear on this one. This is a horizontal. On this function, are there any local extrema? Actually, this is really everything. In fact, given any point, this is the biggest kid in the neighborhood because I use less than or equal. So technically, this is a local what? It's also a local min. So this is Jim's patented stupid example today. Every point on this is a local maximum, a local minimum, and it's an absolute maximum, and it's an absolute minimum, right? Because this is just a really kind of stupid. You notice every point on here, local maximum, local minimum, also absolute maximum, absolute, right? It would have been different if I had restricted all this. Let's look at one that's a little bit more interesting than that. Let's just. Okay, let's see. I would think right here, we. I'm gonna mark it black. Local minimums. How many, I want you guys to look at, how many local minimums do you see? I see five, it's a bit of a joke, but this is a local minimum, right? Smallest kid in the neighborhood. Local minimum, smallest kid in the neighborhood. Local minimum, smallest kid, and I would maybe see that. Smallest kid. Black. I mean, this one right here, that's a great question. I would not, and this is, we could squabble over this, but I will define this as class, because part of it is when I define a local extrema, I want it to be this interior. I want it to be inside it. So it's a great question, right? What about the endpoint? Even if it seems like it's a local min, I'm gonna say it's not if it's at the endpoint of it. Okay, how many local maps? Um, I would call this about the same rule before. This is again, so I'm not gonna, this was not, and this was not even, there's no point there, right? Under this one, big kid in the neighborhood, big kid in the neighborhood, and so is this one, right? Because certainly it's bigger than stuff on this side, bigger than stuff on this. And there's one more at the top of this. All right, so are you asking about this one versus this one?
Oh, that's it.
Yeah. Yeah, you okay with that? Everybody? Okay. Okay, so absolute extrema means it is the king, right? It's the biggest and the small. Local extreme means, it's sort of like the, instead of being the WWE champion, it's like the Intercontinental champion. It's sort of in the neighborhood, it's the big one. Here's the theorem. I want you to look at these pictures, and you might be able to help me out. This is an incredibly important theorem. It's going to drive sort of the applications. And I'm actually going to show you why this was true. Theorem. The extreme value there requires a little bit more mathematics than we're ready to do yet. However, this one we can show. If C f of C is a local extreme, f of x, and f prime of C exists, then f prime of C. What do we guess? Okay, so I want to go back over this example again. So I've got five of these black points that are local minimums. 1, 2, 3, 4, 5. For how many of these two sit at points where the derivative exists? I agree with you, right? Notice that these three ones in the middle, the derivative doesn't exist. It's a sharp point. But here it looks like you could get a nice tangent line of some sort. There's 4 local maxes. How many of them does it look like the derivative exists at? I agree. Again, 2 point, not even continuous, right? But here, anybody want to fill this in? If the derivative exists, it must be. No, well, see, that's, if it exists, then that prime C must be right. But the slope of tangent is at those, at the 2 black points and the 1 blue point where the derivative doesn't exist. Oh. Correct. So I'm going to show you why this is true. Well, suppose first C f of C is a local. So I'll just draw this to illustrate this. C f of C. And there's some interval here. There's some interval in which the y coordinate here is the big kid on the right. Okay, so let's look at what the derivative has to be. So let's just compute the derivative of old school. And old school means you gotta use that one. That's the definition of the derivative. Y'all remember doing a problem where you did this limit from the left side and to the right side and check. Let's do this. 1. Okay, so the only thing that I want to pay attention to is really kind of the sign. What can you say about that age, right? So forget the limit so far, which is this fraction, h is going to zero for the positive side. So what can you say about h? It's always positive. So what can you say about f of c plus h minus f of c? So maybe this is c, and this is c plus h. What can you say about the y coordinate of this function at c plus h as opposed to the y coordinate c? Which one's bigger? The one at c is bigger, right? So when I take f of c plus h minus f of c, this is negative, isn't it? Now, this limit is f prime of c, but it's a limit of negative things, negative over positive, right? So this is less than or equal to zero. Do I agree with that? I haven't figured out what it is, but I know it's less than zero. So now let's check it from the other side. This time, notice that this is still negative. The denominator, or I'm sorry, the numerator of this is still negative because f of c is still the big kid on the block. I agree. So the y coordinate here is smaller than the y coordinate here, and you get a negative. Well, what's h now? It's also negative. This limit is f prime of c. But now this is a limit of negative over negative is positive, so it's greater than zero. So we know by assumption this number exists, and we know that f prime of c is less than is greater than is less than or equal to zero, and it's greater than or equal to zero. And I know of only one number that's both less than or equal to zero and greater than or equal to zero. What is that? This one. Your hand is force. Now, I only showed you this for local max. Try this for local min. Well, it's the same thing. So that basically times the same. This is why this works. That's essentially it, right? I mean, that's essentially the same kind of idea. Yeah. So let me give you a corollary to this, a spin-off. Well, this is if C f of C is a local extreme of f of x, then f prime of C equals zero, or f prime of C does not exist. This is a very important theorem because it basically gives us a way to find local extremes. And if I draw a function, this, I'm gonna mark local extreme here. Here it is, local max. every black point is a local max. I agree. This one right here at the joint point here, if you will, it certainly is the kid in the neighborhood. It beats everybody to its left and it ties everybody to its right. That's good enough. Right. And in blue, I will have my local men right here, right here, right here, and those all the blue points from local men's. Smallest in the neighborhood, smallest in the neighborhood, smallest in the neighborhood. The joint point is the biggest in the neighborhood, and it's also oh, state. There we go. This joint point is greater. It beats the people on the left and ties the people on the right. This one actually can't be a local men, but everything over that. This is notice at the black and blue points, derivative zero, derivative zero, derivative zero, derivative doesn't exist, doesn't exist, doesn't exist, doesn't exist at the corner point, right? And everywhere across here, derivative exists in a zero. It's flat piece, and derivative zero. So that's what this is saying. This is incredibly powerful because if you're on the hunt for local extreme values, which is what you need to do, so this will help you graph the function. Then all you have to do is look for places where the derivative is zero, there's no existence. And here's why it's important. Suppose I want to know what a function looks like. I need to know this because it's telling us about the weather, my bank, some physics with an asteroid, whatever. Suppose I know there is a local max, local min, a local max, and it's continuous everything. I can tell you roughly what this looks like. It's a local max, local min, local max. Now there are some subtleties I don't have to what this function looks like. For example, after here, it could indeed go something like this. Or after here, it might be much steeper. There's other things that happen. But if those are the only three points of local extrema, I've got a pretty decent idea of what that is. Okay, and now let me give you one final definition, and then I'm going to go very final. So do a lot of definition. And be take a little bit of care with this definition. Say what I mean. Let's see the interior point. Domain. And all I mean by that is I just don't want to see B at an end. Right, so we'll assume we're done with this. So, if f prime of c is 0 or f prime of c does not exist, we say c f of c is a critical. Some authors just say that the x coordinate is a critical point. I would rather say that the whole point is a critical point. But sometimes I'll try to. Now, let me point out that so bit of a definition, but it says, notice we're assuming that a critical point is actually in the domain of the function. That is to say, you can plug in the x value into the function if it makes sense. For example, you look at the function 1 over x. 1 over x, you can't plug in 0. 0 is technically will never be a critical. Nonetheless, we can sometimes use that point in the analysis. For here, what I'm going to do is, let me remind you of this theorem. If f of x is continuous on the closed interval, then f of x contains max in balance. I gave you this theorem a little bit earlier, and it might have occurred to you at the time, well, it's very well in the theorem, and I did say that it was beyond the scope of what we're going to do to prove this. So maybe this is sort of intuitively obvious, but it's hard to actually really be careful about. But there's a very easy procedure for finding this, and I'll show you what it is. Suppose that f of x on some interval. So I'm going to outline the procedure to find the maximum. This is very important because you're getting optimal value. So suppose I just walk up to you on the street with a good function f of x. Say, okay, I want you to find me the biggest and smallest values. So number one, of course, I guess I am assuming that it's most differentiables. But that is differentiable on most of that interval. Find a derivative. This is calculus. 2. Find the critical. So take the derivative. That's something you've been doing for a while, and now you're actually going to use this. Find the critical. How do you do that? Find places where the derivative is either 0. So take that derivative, set to 0. That's the solution. And find out where it's undefined, if possible. So now, we'll call this critical C1, C2, C1. So maybe you've got 100,000. Maybe you've got 0. Here's the rub. If this thing this function has a maximum minimum value, so it has to occur at one of these critical numbers. It has to occur at the top of the mountain, or the bottom of the valley, or there's 2 other places where it's. It could occur. So all you got to do at this point, once you wrap up the critical, all you got to do is plug it in. Have a confidence. F of C1, F of C2, F of Cn. Plug this into the original function, of course, not the derivative, because plugging the derivative between 0 it doesn't exist. And plug in the endpoints. That's it. When I say contest, big 1 or 1s is max, one or ones. That's it. So let's do something. I think you'll find this. It's a world's most boring guy, but I kind of find it fun. Hopefully you will too. Once you get going and see how this is really not too bad to him. So let's start with this example here. Let's look at x cubed minus 3x squared. So my instructions on all this will be basically finding extreme values. Okay, so I don't even have to draw a picture. All I gotta do is follow this procedure. One, f prime of x. Tell me out. What's the derivative of this thing? Three x squared minus 6x, which is 3x x minus. Right. What are the critical numbers? Yes. There are places where the derivative is 0 doesn't exist. So what do I got? 0 and 2. And this exists everywhere, so there's no, does not exist fundamentals. Critical numbers are x equals 0. And they were both in. What if one of the critical numbers I got was 5? What if I had gotten 0, 2, and 5? Just wouldn't use 5 because 5 is not an interval I'm concerned. But both my critical numbers fell between -1 and 3, so I need to do. Now, have the confidence. F of 0 is 0. F of 2 is -4. And I'm going to check even. F minus 1 is -4. And F of 3 is 0. Huh. Max. Then what are my maximum and minimum values? The maximum value is 0, so this thing is never positive. Biggest you can get is 0 on the interval from -1 to 3, and it attains its maximum at 0, which is inside, and its right endpoint. And its minimum is -4, and that occurs twice as well. So if I were to sketch this, -1, 0, 1, 2, 3. At -1, it's -4. At 2, it's -4. And at 0, 0, and 3 it's 0. So it looks something like this. Right. Right. How about this? X to the 7/3 plus 28x to the 1/3 find the extreme values of this. I only did that to make my computation a little bit easier when I plug it later. It was like, well, let's see what third out of this. So, let's take it for it. So, this 7/3, takes 4/3, and I get 8/3, makes my. Here's a groovy little trick. So maybe it's, so at this point, I'm gonna find out where the derivative is zero run, the zero run. Well, this gobbledygook is probably not here. But this is where, you know, the gospel I gave you earlier, don't simplify something unless it's something for you. There's something in it. I'm gonna pull out 7/3 x to the minus 2/3. So I'm gonna pull out the biggest, there's a factor 7 in the numerator, factor 3 in the denominator. I'll pull out the largest negative power. Notice this leaves me with -4 here. Here's a good way to get check. So I'll multiply this back and -20 x. Let's see, pull the 7/3 out of this first one, and I pull the -2/3 out of this, so that's like adding 2/3 back. And the good thing about this, you can always change something back. This is gonna be 7/3 x to the 2 minus 2/3. Then it's gonna be -2. This to me makes it a lot clearer. You all see the critical numbers now? What is this check? And what about this one right here? Notice this one is the break. Because this is really like x to the 2/3 in the bottom. So these two give you zero derivative. This gives you derivative not zero, or this gives you derivative not. Now I can toss one of those critical. Which one? That is correct. Toss this. It's not in there, so I don't worry about that. So really, here's the deal. I got two critical numbers and two. So now we have contest. Let's look at F of 2. And now using this to do That's gonna be, this is gonna be 4 minus 28 is minus 24 times 2 from 1/3. When I plug in 0, when I plug in -1, I get, that's going to be minus 27 minus 1 is 27. And when I plug in 5, I get, see, 25 minus 28 minus 3 times 5 to the 1/3. Oh, dear, oh, dear, I don't think I'll do it. So, I bet you guys probably put your eyeballs on, tell me who's the winner as far as the bid, who's the bigger? Okay, this one's gotta be mine. Who are my candidates for this? That's right, so, well, be careful, this is where they occur, actually, the minimum value will be whatever the Y one is. It zeroes out of the context, right? Because I know the negative, which one is more negative, which one wins? I agree, how can you tell? Well, so notice that this is minus 24. 2 to the 1/3 is actually a little bit bigger than 1. So this is actually smaller than negative 24, right? And this is actually bigger than negative 6, right? Because 5 to the 1/3 is quite 2, right? So the most negative this could ever be, it's actually not quite as negative as 6. So I don't have to know the exact number to know who wins the contest. You're right, it's this is thin. Everybody okay with it? Okay, some sports. Let's do one, let's do kind of a different. Let's see if we can figure this out. This isn't really my contest. We'll put this on the. Remember, on an infinite interval, you may not have extreme values. It's possible this thing looks like this. So then you never got a minimum maximum. So let's investigate and see. So, okay, this isn't in the procedure that we described before because this isn't a finite interval. And it's not even closed, right? You can't really plug into, so you can't really plug into this. But let's look at the critical. Because I know that if there's a local extreme value, it has to occur, whether or not that's a finite interval, what, but a local extreme value has to occur, they're critical. So I'm gonna find the derivative of this, what's the first thing that you do? I should take a log of this. I took a little extra step. The log of this, and then I brought the x. Does everybody know what it is? So let's take the derivative of this. 1/y, y prime. Let's take the derivative of this. Oh, by the way, I wanted to tell you all that, I'm taking your derivatives. Most of you taking the derivative, pretty good. The score is pretty sound. In fact, the most common thing that you mess yourself up with is not really the calculus, but the algebra. So I'm very pleased about that. So just those skills up and work on simplifying. Well, not simplifying, but work on being careful about algebra steps, the necessary. So take the derivative of this when you product it. So it's going to be 1 times natural log of 2x plus x, 1/2x. That's a derivative of 2x. Exactly. And this turns out to be this log 2x plus 1. So we get y prime is y times log 2x plus 1. So I get 2x to the x. Natural log 2x plus 1. Okay. If I want to understand what this function is doing, as I pointed out before, it might help to find the local extremes. And let's see, the local extreme should be corresponding to find where this thing is either equal to 0 or doesn't exist on that interval. 0. 5. Now, where does this does not exist? Nowhere. Because on the interval from 0 to infinity, not including 0, this is always continuous, so is this. So DNA doesn't happen. So you only need this to be 0. Well, this piece can never be 0 either. You never take some number x, double it, and then take it to that power and get 0. That's impossible. You're putting 0, right? Because you will have a positive power of a positive number. So it's the other term that must be 0. So I get natural log 2x negative 1. Now take the exponential of both sides. Well, the whole point of this is what is e to the log of 2x? So I get x is equal to 2. That's the only good thing. There's only one. At this, see, 2 over e, 2 over e power. Four over e to the power. Now, we'll care what the is. Bottom. Make a mistake, just get it. This is two X, one E. So this is X, two L better. So this is like roughly somewhere between the 4 and the 6. And F of 1 over 2E is 1 over E to the 1 over 2E. Notice, by the way, it's less than 1. Notice you're taking basically 6 root of something plus 1, it's plus 1. So actually what this function looks like is you have one critical number here. Notice what happens to this function when x gets large, it's getting huge. Do you agree with that? So question was, what are the max min values on this? You get a minimum. And it occurs at 2 over E, sorry, yeah, 1 over 2E and 1 over E, the 1 over 2E power. This is your min value. It goes down to that and then up forever. There is no maximum value because as you go off display, it's slow. Okay. Any questions on that? Here's by the way, I guarantee you on the next test and final, and maybe some other places along the way, this is a very practical kind of problem. Make sure that you practice these. Make sure that you practice a lot of things tonight. Be good at it. Procedures, not bad at all, but it takes getting used to it. This is a nice little tree function. It's periodic. Its period is certainly no more than 2 pi. So I want to know this. I want to find maximum. On the center 0 to 2 pi. And by the way, if I find the extreme values on 0 to 2 pi, I found the absolute extreme values everywhere because this function just repeats over and over. Right? So whatever its extreme values are on the interval from 0 to 2 pi will be carbon copy. Right? Step 1. Take the derivative. Derivative sine of block, cosine of block, derivative block. Derivative minus 2 cosines. Derivative is easy again. Right, okay. The hardship we face at this point is, well, what is the hardship? Gotta find the critical numbers. Those are places where those are places between 0 to pi where this is either 0 or does not exist. Now, does not exist doesn't happen for this particular one because this function is continuous. 0, that's a problem. What's the biggest problem that you all see? Finding, if this were 2 cosine x plus 2 sine x, I could solve for this and get in. This is a cosine 2x, right? Which makes this how might we tackle this? By the way, trig identities, the one trig identity I expect you to remember is this. Sine squared x plus cosine squared x is one. Any other trig identity, and I expect you to know what the trig functions are, like if I say secant, you should know that one over cosine. Any other trig identities, we can give it to you free of charge. And I'll put them up there and say, boy, I'd really like you to tell me double angle, it's free. Right? That's what I'm gonna use. Cosine 2x sine squared minus sine squared. And you can also rewrite this as 1 minus sine squared. That you can also do that with cosine squared. I'm going to focus on this. And the reason is because I've got a sine here. I'd like to show this sine. I said I did it to cosine 2x. Now, set the sequence. So 2 minus, well, 1 minus 2 sine squared x plus 2 sine x. I'm gonna divide, I'm gonna multiply this by minus a half. So it's 2 sine squared x minus sine x. But reading so far. But now, oops, what do I do now? That's your quadratic equations to solve it. More than that, works out nicely. Let me make this a little bit simple. Let me just do a temporary substitution. Everywhere I see a sine x, I'm going to call it u. So this is going to be 0 is equal to 1. That's a u. And how would I write this? 2 times what? Y'all see how to factor this one? You can always use the quadratic formula. This one factors. U squared minus 2 equals minus 2. So my solutions here are u is minus 1/2. Right, that's making the first one 0 and the second. And remember, u is sine x. So I have to solve the following equations. Sine x is equal to 1. And sine x minus 1. Okay with that? Okay. Circle trace. Spelling x equals 1. And here, remember, x is 0 and 5, because that is the interval. Where's the sine x equal to 1? Right, and that's the only place, isn't it? Only up here. There's more of my critical. X is not over, right? What about the other ones? I think most of them. Good. It actually happens 30 degrees beyond here and 30 degrees before you get to the end. Right, and sine x is minus 1/2. That means the y corresponds to that, so it should be these two. It should be x equals 7 pi over 6, and then right before 2 pi, so 11 over 6. So let's just call this out. In f x is sine of 2x x 2 plus x. So let's take power 2 first. Sine twice that. Minus 2 cosine of 2. Notice the sine of pi is 0 as is the cosine of pi, which is 0. F of 7 pi over 6 sine double this minus 2 cosine 7 pi over 6. All right, in this case, 7 pi over 3 is 6 pi over 3 plus another 5. So that's just 3. This is where 7 pi over 3 would be right here. So what's the sine of that? Root 3 over 2. Minus 2. And cosine of 7 pi over 6, what's the x coordinate of this? I guess it's minus root 3 over 2. Which I guess comes to 3 minus 3. F 11 over 6 is sine 11 pi over 3 minus 2 cosine 11 pi over 6. Now 11 pi over 3 is, well, let's see, I guess that's 12 pi over 3, which is 2 pi. Take away pi over 3. So 11 pi over 3 is right here. So its sine is negative. Right here. And the cosine of 11 pi over 6 is positive right in the 3 over 2. So I get minus 3 right. Now, let's check the endpoints. What happens at the endpoints? Let's go with the sign of 0 minus, let's go with minus 2. This should be at 2 pi. Period. So now I've got it. Okay, so what's the minus? So this. That. This max should be fairly obvious. What's the min? But here's what we put 7. So this is a little bit more than 5 over 2. I think this is actually small. But here's another way to check. What happens when you square -2? What do you get? 4. What happens if you square this? You get like 27/4, which is actually bigger than 6. It squares to something bigger, so this has to be larger. Okay, any questions on it? Okay. Well, you feel like you understand the procedure for all this? All right, next time, if you look at the syllabus, next time we're going to do section 4.2 and get a little bit into 4.3 as well. The next section is mean value theorem, which we could go through fairly quickly, although the mean value theorem is terribly important. We'll get a little bit into explaining what derivatives do for us. It's time to take a quiz, and so we will do so now. Don't forget, you can come talk to me at any time up to for the next test. That extra 10 points if you want to discuss where you're at.